Thyristor turn on. A thyristor is turned on by increasing the anode current. We have different types of turn on process. First, thermal. If temperature is high, there will be an increase in number of electrons, holes, pairs. This will increase leakage current. The increase in the current would cause alpha 1 and alpha 2 to increase. Due to regenerative effect, alpha 1 plus alpha 2 tends to unity, and the thyristor may be turned on. Disadvantage is thermal runaway. So we avoid this type of turn on mechanism. Then the second one, light. If the light is allowed to strike the junctions of thyristor, the electron hole pair increases and the thyristor may be turned on. Since electron hole pairs increases, the leakage current increases, which again increases the alpha 1 and alpha 2. So by regenerative effect, alpha 1 plus alpha 2 tends to unity, thereby thyristor is going to turn on. So the light activated thyristors are turned on by allowing light to strike the silicon wafer. Light activated thyristor will use this type of turn on process. Then the third one, high voltage. If the forward anode to cathode voltage is greater than VBO, that is forward breakdown voltage, significant leakage current will flow to initiate a regenerative turn on. And this type of turn on may be destructive and should be avoided again. Fourth type, a dV by dt turn on. If the rate of rise of anode to cathode current is high, the charging current of the capacitive junction may be sufficient enough to turn on the thyristor. Since we have the relation the charging current of the capacitor junction may be sufficient enough to turn on the thyristor. A high value of charging current may damage the thyristor. The thyristor must be protected against high dV by dt, and the manufacturer specifies the maximum allowable dV by dt of a thyristor. The fifth type is gate current. If a thyristor is forward biased, the injection of gate current by applying a positive gate voltage between the gate and cathode terminals would turn on the thyristor. As the gate current is increased, the forward blocking voltage is decreased. You can see as the gate current, so that Ig1, Ig2 and Ig3, where Ig3 is greater than Ig2, Ig2 is greater than Ig1, gate current is increasing from Ig1 to Ig3. So as the gate current increases, the VBO naught is decreasing, and there is a time delay known as a turn on time between the application of gate signal and the conduction of the thyristor. So T on is defined as a time interval between 10% of steady state gate current and 90% of steady state thyristor on state current, that is IT. The turn on time is again divided into two parts, or by adding these two parts we can get the turn on time, that is a delay time and a rise time. Delay time is from 10% of the steady state gate current to 10% of the thyristor on state current. Rise time TR is required for the anode current to rise from 10% of the IT to 90% of the steady state turn on thyristor current. Combination we can say, and this point is same. So from here to here we can take that 0.1 Ig2, 0.9 IT is nothing but the turn on time. So point should be considered while designing gate control. The first point is gate signal is removed after the thyristor turn on. A continuous gate signal would increase the power losses in the gate junction. Now, second point, no gate signal and a reverse biased. Otherwise, the thyristor may fail due to the increased leakage current. Third point is the width of the gate pulse Ig must be longer than the time required for the anode current to rise the holding current value IH. In practice, the pulse width of TG is normally more than the turn-on time of the thyristor.